delay the schedule?
Yeah, maybe we should wait a little bit.
Yeah, but then I will try to shorten the questions. To create a question.
But maybe we distract.
Yeah, but I think we should definitely be on time for lunch, right? Because if all the people going there, otherwise they will get messed up. I don't know what Benedict was saying about that. We should be in time for lunch.
Yes,
That's important.
yeah. So we should not wait too much. I don't know.
Because they serve, I think it's like yesterday, to serve everyone.
Yes.
And then if you're, yeah, if the groups are in different time, in fact, it should be more.
Yeah, it is, yeah.
So everyone can. Everyone can unmute. Then, so they can unmute themselves.
Message to the network. Or it's blocked.
For that reason. We are here. We are here.
Do we need to do something? No. Okay. That's the problem.
Yeah, we have this one that probably is the best. You can move. Yeah. I will do.
I can push you.
You can have this one all the time.
Okay, let's start. Welcome to the second session of the day. It's about fast, efficient hardware implementations. We have 4 talks in this session. And the first one is CF NTT, Scalable Radix-4 NTT multiplication architecture with an efficient conflict-free memory mapping scheme. This talk will be an online talk, and we will now start the video, and afterwards the authors are available online to answer your questions.
Tsinghua University. It's my pleasure to give this presentation about CF NTT. CF refers to conflict-free memory mapping scheme. I'm going to talk about a scalable entity multiplication architecture. This presentation is organized with 5 parts. First, we introduce some backgrounds. The module learning with arrow-based scheme, such as Kyber, could be divided into 3 stages. At the stage of key generation, the public keys are A and B, the secret key is S. At the stage of encryption, the public keys are used to encrypt the message, then the ciphertext U and V are obtained. At the stage of decryption, the secret key is used to decrypt the ciphertext so that the original information is recovered. Obviously, the polynomial multiplication mainly dominates the entire scheme. There are 3 classic methods to compute the polynomial multiplication. Since NTT can reduce the complexity from quadratic to quasi-linear, it is widely used to accelerate the polynomial multiplication. NTT transforms the coefficient vector to the point value. Then the point-wise multiplication is performed. Finally, the inverse NTT transforms the point value into the coefficient vector to obtain the final result. The polynomial multiplication over the ring needs extramodular reduction. To ensure the existence of 2n roots of unity, the modulus should satisfy this condition. But if fx is equal to this one, we can use the negative wrapped convolution to avoid extramodular reduction. While the so-called pre-processing and post-processing can be eliminated by merging factors into every stage, the powers of nth roots of unity omega will take part in the NTT and INTT computation. The Radix-2 butterfly unit is the basic operation of NTT, which can be classified into 2 types. In pipelined NTT architecture, temporal conflict occurs when the read operation is performed before the write operation in the former stage. This figure provides an example for this read after write conflict. The pipeline depth ought to meet this condition to avoid this conflict. This condition will become more stringent when considering the higher radix. If multiple data points are mapped onto the same bank, we need to perform several read or write operations on a single bank address simultaneously, which results in the so-called special conflict. Join proposes a memory mapping scheme for arbitrary radix in place FFT. This scheme is not suitable for the case when placing multiple butterfly units in every stage. This special conflict is shown in Figure B, using 8-point radix to FFT with 2 butterfly units as an example. Considering the 3Ds, namely diverse security parameters of cryptographic scheme, different resource constraints of computation platform, and different throughput requirements of practical application, we focus on the 2 metrics, scalability and aerial time performance. As for the scalability, 5 dimensions are taken into consideration. T denotes the types of entity, while entity with in-place property has varying stress and complex axis pattern. N denotes the length of coefficient vector, and Q denotes different prime moduli. This can be regarded as design time parameters. Finally, D denotes the number of butterfly units, and R denotes the arbitrary radix. These 2 parameters are seldomly considered at the same time. The axis conflict becomes more complicated in this situation. As for the aerial time performance, our goal is to minimize the value of aerial time product. Therefore, we try to reduce the algorithm complexity to decrease both latency and aerial cost. To seek a sound balance between aerial and time, we explore the design space to find the most efficient design strategy. Then, we introduce the derivation process of optimized Radix-4 NTT and INTT algorithm. For Radix-4 NTT, the pre-processing can be avoided by merging the roots of unity into every stage. First, the pre-processing and the main entity are written together as below. Then, by splitting the summation into 4 groups according to index j, the equation is transformed as this one. By leveraging the elimination property of triple factor, the equation can be simplified as below. For simplicity, let 0 to F3 denote the 4 summation items. By applying the periodicity property of triple factor, the other 3 equations can be obtained in matrix form as below. By adopting this divide and conquer strategy recursively until n equals 4 points, we can obtain the Radix-4 NTT algorithm. Up to now, we eliminate the 2n modular multiplication completely. By merging the corresponding factors, the post-processing of Radix-4 INTT can also be cancelled. At the very beginning, the post-processing and the main INTT are written together as below. According to the index j, we can split the summation into 4 consecutive groups with the same size n pools. Based on the periodicity and binary property of triple factor, we can put the 4 summation items into the same range. Because of the elimination property, the equation can be simplified as below. Note that these 3 factors can be classified into 4 cases according to the index I. As a result, the equation can be grouped into 4 parts. With the elimination property of triple factor, the first part can be further written as this one. For simplicity, let G0 to G3 denote the 4 summation items respectively. With the sum and binary property, the equation is further expressed in matrix form. By adopting this strategy recursively until 4 points INTT, the n-modular multiplication is removed. It is easy to see that some immediate results can be reused when calculating the radix-4 butterfly operation. Thus, we schedule the matrix multiplication into 2-layer operations as below. At this time, the modular operations in Radix-4 butterfly unit are reduced to 4. Similar to Radix-4 NTT, the complexity in Radix-4 INTT butterfly operation can also be further reduced. Thus, we schedule the matrix multiplication to reuse the immediate result. In this way, we just need 4 modular operations, which results in the 2-layer gentleman sand butterfly unit. The bit reversed operation is needed in classic NTT and INTT operation. To avoid the bit reversed cost, we propose a generic method for Radix-R entity. The first step is to reverse the first loop to generate the input address with natural order. To still obtain the correct results, the generation of triple factors is required to rearrange accordingly. So the second step is to replace the powers n divided 4j with powers j, and replace the index j with bit reversed index k. The final step is to move the place of generating triple factors from the innermost loop j to the middle loop k. Finally, we obtain the complete Radix-4 DIT-NR entity algorithm, which consists of 3 nested loops. In the hardware implementation, the triple factors are usually pre-computed and stored into the ROM. For inverse INTT with Radix-R, we also try to propose a generic method to avoid the bit reversed issue. Based on the DIT-NR entity, we can obtain the DIF-RN INTT by just reversing the first loop and replacing the triple factor with its inverse element. However, double memory footprint is needed for storage of trivial factors based on this method. Thus, we try to reuse the trivial factors of forward NTT to reduce memory footprint. Based on the binary and elimination property of trivial factors, the first optimization technique is to derive three new tricks as following. Then we apply the derived tricks to obtain the inverse trivial factors by reusing the forward trivial factors. Finally, we obtain the complete DIFR INTT by modifying two-layer Radix-4 JS butterfly unit. By now, the 50% memory footprint of trivial factors are saved. Next, we present the proposed conflict-free memory mapping scheme. At the very beginning, we determine the way how the data points are managed in parallel computation, taking DID NR Radix 2 NTT with two butterfly units as an example. The 8-point data flow along with index set pkj is depicted in this figure. The 4 data points at stage 1 can be parallelly accessed into two types of order. In order 1, 4 data points come from the same group index. In order 2, 4 data points come from the same round index J. In this table, we determine the order 1 as the case study. We propose the generic parallel NTT algorithm with arbitrary radix based on the determined address order. We apply the loop on row method to obtain two loop tails. The range of index J and K in the inner loop and middle loop depends on the index P in the outer loop. The relative size of D and J will influence the number of iterations. As a result, the loop on row method is classified into two cases. If J is less than D, the parallel data sets will contain several iterations of inner loop. Otherwise, the inner loop will contain several parallel data sets. For brevity, the address generation method is kept. To address the special conflict, we propose a new and efficient memory mapping scheme. This figure presents the hardware structure of a memory mapper for arbitrary radix. The address is divided into the lower part and the higher part. The lower part is expressed in radix R and generates the step number based on modular accumulation. The higher part is expressed in radix B and generates the bank index based on modular addition. This scheme can support automated configuration. It can be initialized for different radix and facilitate other stride access. We further extend this method in our paper at DEC 2022. We further make a case study of 16-point radix to in-place entity with two butterfly units. The 16 old addresses are expressed as mixed radix. The so-called step number is obtained by accumulating the digit in the higher part of the address, following a modular reduction by 2. The value of slide distance depends on step number and the step size. Finally, the bank index is obtained by adding the lower part to the slide distance, following a modular reduction by 4. In addition, we can further reduce the number of banks from 4 into 2 by merging the addresses. Then we briefly describe the proposed hardware architecture of Radix 2 and 4 NTT. The address generator calculates the logic addresses based on configurable counter and shift operation. The memory mapping unit generates the physical addresses and can support different radix and parallel degree. The interconnect network synchronizes the parallel data points without pipeline store. To increase the computation throughput, the interleaved memory banks are used. The trivial factors of NTT are pre-computed and stored into a row. In this architecture, just n-1 words are needed. The Radix-4 P array is unified to perform NTT and INTT based on the configurable routing structure. This table lists the number of operations within each processing element. In total, the number of modular multiplier is 4. The number of modular adder and subtractor can be set as 4 or 8. If we set the multiplexer control signal to 0, then NTT is performed. Otherwise, NTT is performed. The modular multiplier is based on Barrett reduction. The multiplication by fourth root of unity is a constant modular multiplier within P3. Finally, the implementation result and comparison is given out. This table shows the theoretical difference between Radix-2 and Radix-4 NTT in terms of hardware resources about some common module. The Radix-4 NTT consumes the same number of cycles with Radix-2 theoretically, but it only needs half number of banks when configured with the same number of butterfly units. Additionally, if the constant is small in Radix-4, the multiplication complexity is reduced compared to Radix-2. The proposed architecture is implemented on the Vertex 7 FPGA. This figure with dual coordinates depicts the comparison of ADP measured by LUTs, FFs, and the number of DSPs BRANs between Radix-2 and Radix-4. When setting the number of butterfly units to 8, the ADP of LUT FF in Radix-4 NTT core is approximately 2.2 times or 1.2 times less than the Radix-2 NTT core and consumes less number of BRANs. Finally, we mainly compare the implementation result of Radix-4 NTT core with the state-of-the-art works. The aerial time performance of the proposed one has a clear advantage over other works. Thanks for your listening. Our reference codes are up in this website. Questions are welcomed.
Everyone can Okay, the speakers kindly agreed to be available online in case there are any questions. No one? Yeah, let's see if there's a question online. No, okay, then I have a small question for the speakers. You mentioned some follow-up work you presented also this year. Can you shortly summarize in 2 sentences for all of us what you are doing there and what is the improvement? You need to unmute yourself now.
Okay. Well, thanks for your question. In our work at DEC 2022, we further extend the conflict-free memory mapping scheme. In summary, we mainly present heuristic to explore the design space of conflict-free memory mapping scheme, which is suitable for arbitrary radix of NTT. We also design a NTT hardware accelerator for deleting, which achieves a good result. That's all. Thank you.
Thank you. Are there any other questions in the meanwhile? Okay, no, then let's thank the speaker again, and we move to the second presentation of today.
Yeah, okay.
Okay, so the second talk of today is about quantum period finding against symmetric primitives in practice. And Xavier will give this talk.
Okay, thanks for the introduction and welcome to the quantum circuits part of this session. So first of all, what do I mean by practical computing or quantum computing in practice. It comes from a general issue we have with quantum attacks. It is that, as you probably know, quantum computer as of this day don't work that well, which means that when we devise a quantum attack, we can't really run it. And in the analysis, we often only care about asymptotic behavior, which only gives us part of the picture. So what we did in this paper is to propose complete quantum circuits for the offline Simons algorithms in order to have a better understanding of this attack. This will also allow us to get some meaningful comparisons with other quantum attacks besides asymptotic. So for concrete instances, we can compare them, and this will also allow us to study the limitations of the attack. So what makes it less efficient or even not applicable. So now, in more details on what we did, we wrote our quantum circuits in Q#, which is a dedicated languages for quantum circuits. This language has the it allows to produce quantum circuits with quantum gates that are the analog of classical logic gates. And Q# has the advantage of allowing us to efficiently simulate and test a classical subset of these quantum gates. So for some quantum circuits, we have some very efficient simulation, even if the circuit requires a very large amount of qubits. So even for thousands of qubits, which for general quantum circuits is not possible. It also provides some resource estimates, and so our results will be some resource. Typically, it will be estimate the width of the circuit, so the amount of qubits. It will also estimate the depth, which matches roughly the time of the circuit if we assume everything is parallelized. And we also can get the total amount of gates and so on. And if you're interested, the source code is available online. So now, in more details, to present the offline Simons algorithm, I first need to talk a bit about Simons algorithm. It is one of the first quantum algorithms that have been proposed in the literature, and it aims at solving a simple problem, Simons problem, where we have a function f on n bits, and this function is periodic. That is, there exists a value s such that if you add it to the input, it doesn't change the output. And the aim of the problem is to find this secret period. Classically, this problem reduces to collision finding. So the best we can do to retrieve the period is just to look for a collision into the n over 2 queries. But quantumly, we can do much better thanks to Simons algorithm, which only requires a linear amount of quantum queries and some polynomial post-processing. Now, a bit more detail on what Simons algorithm does. First, Simons algorithm requires what we call quantum queries or superposition queries. That is, the ability to compute from a superposition of input, the superposition of input-output table for the periodic function. And if we're able to do that, then we can sample random values that would be orthogonal to the period. And from that, it's easy to recover the period by simply repeating this process a linear amount of time and do a bit of linear algebra. So now, how can we apply that to cryptanalysis? Here, I will present to you the Even-Mansur cipher, which is often devised as the simplest possible block cipher. It's constructed from a public random permutation P, and to encrypt a message X, you just add the first key, apply the public permutation, add a second key, and you have your ciphertext. And classically, this very simple construction has a security proof. That is, for a random permutation P, any attack requires a certain amount of time and data, such that their product is at least 2 to the n. However, quantumly, it's extremely different because we can construct a periodic function from the Even-Mansur construction. It's simply adding the encryption of a message X and the image through the public permutation of the same X. And it's fairly easy to see that it is periodic, because if we add K1 to the input, we can simply push it forward to the 2 branches, and it only amounts at swapping the 2 branches. So it doesn't change the result, which means that from this function, we can apply Simon's algorithm and recover the secret key K1 and breaking the cipher. So the event mentor cipher is broken in polynomial time, but with quantum query access. That is, we need the ability to compute this function that depends on some key material in quantum superposition. So this is a very strong model, and that's not really applicable to this day. And now what we want to do is to have an attack that will work only with classical messages and classical queries. And this is exactly what the offline Simon's algorithm does. So the first idea to move from quantum queries to classical queries is fairly simple. We can construct the quantum state that corresponds to a quantum queries if we know all the classical queries that it contains. So if we have the full codebook from this function, we can apply Simon's algorithm. Of course, the full codebook is fairly large, size 2 to the n, which is more than the cost of the best classical attack. So it's not really interesting to do that, but it's a good starting point. And if we want to have something efficient, what we can do is to split the input in two parts, and only we will fix the input on n minus u bits and only consider a function of u bits. And if we do that, we can still craft a periodic function. The only difference compared to before is that we need to know the value on the key on the part of the input we've fixed. So now, from that, we can make an efficient algorithm, which will be in two parts. So we will have Simon's algorithm on the part of the input that's variable. But in order to apply it, we need to know what is the value of the key on the other part. And so we do a quantum search on the value of the key. And the test to know whether the key on the part of the input is fixed, is correct or not, is to try to apply Simon's algorithm. If it works, it's a correct key, otherwise it's not. And so for this attack, in terms of cost, we have a data cost of 2 to the u, which is the classical cost to get the full codebook on u bits with n minus u bits that are fixed. And the time cost will be 2 to the u, which is the initial quantum cost to produce the quantum states that we want. And then the 2 to the n minus u over 2, which is the cost of the quantum search on n minus u bits. So the part of the key we need to guess. And the nice part also on this algorithm is that it's polynomial in memory. So this balances at 2 to the n over 3. But here I only have some asymptotical behavior, and now I'm interested into understanding what this BGOS hides. So now I will detail more the quantum circuits that we've devised, and this is the quantum circuit we want to implement. This will be the test function for our quantum search. So the input is I, it will be our key guess. And in order to test whether or not this key guess is correct, what we will do is we apply many copies of Simon circuits that we have here on the left. Part of these circuits are computed beforehand from the classical queries, and the other part only depends on the key guess. And each one of them will sample a value that is orthogonal to the period. And so if we have enough of them and do some linear algebra, we would be able to recover the period. However, there's a simple way to do a test, which is that if the function is periodic, then we can only sample values that are orthogonal, which means that they will lie in a hyperplane and they can't form a matrix of full rank. However, if the function is not periodic, then we will only have random values, which means that we will end up with a set of full rank if we do enough queries. So our test for the quantum search is simply to do some linear algebra on these Simon values and check whether or not it is a full rank. So now, in order to have some concrete estimates, we need to know how many queries we do in this circuit. So here we built about upon some previous works that I've done on Simon's algorithm, and the very simple way to see it is that we only need n+9 queries for the periodic functions, and another bonus in terms of memory is that if we truncate the output of a periodic function, it is still periodic. And here, if we only have 11 bits of output of the periodic function, the algorithm would still work as expected. So this this attack allows us to do some specific optimizations. So we have these specific properties, that is part of the input is fixed. We only need part of the output. And the only thing we care about is whether or not a function is periodic. This can directly be translated into some optimizations. So for the input, there will be a shared part of the computation that we can only compute once. And for the last round, we can simply remove the part of the last round that do not affect the bits we care about. So now I will detail more our attack on one of our targets, which is Chasqui. Chasqui is a lightweight Mac. It's also an ISO standard, and it has a data limitation. That is, we should not encrypt more than 2 to the 48 messages with the same key. As you can see on the picture, it has an event sort structure, so we can apply the offline Simon's algorithm on it. And if we look at the details of the permutation, it's an ARX construction, which is actually pretty good for quantum implementations because all of its components are either very easy to do, so the linear part, rotation or XOR, or for the case of the addition, it's fairly standard and they're actually very well studied in the literature on quantum circuits. So now, if we'll have a look at one round of Chasqui, so this is a quantum circuit that performs an in-place implementation of a round of Chasqui. We have the input on the left and it transforms it to the output. And for the first round, we can simply remove a quarter of the round of Chasqui because this is the part of the input that is fixed. And now, if we have a look at the last 2 rounds of Chasqui, so it's just twice the previous picture, we can do even more, because if we carefully choose which 11 bits we want to select, then we can remove almost all of the last round, and we can also, for the last and second to last round, use quantum additions on only 16 bits instead of 32 bits, which is twice cheaper. So overall, with these 2 optimizations, we gain roughly 2 rounds out of the 8 of Chasqui. So now that we have some quantum implementation of the cipher, we also need to implement the linear algebra part of the test. So we needed to devise a quantum circuit that, given a Boolean matrix, so m times n with m that can be significantly larger than n, compute its rank. We managed to do that fairly efficiently by computing a triangular basis and then do an in-place reduction of all the vectors. And we got a circuit that's quasi-linear in depth. In terms of number of gates, it's cubic, but we can see that it's only linear in the larger parameters. And in terms of cubic, we only have a slight overhead because the input is quantum. We have mn bits as input. We can't do better than that. And we add a bit more than that, but it's small compared to the mandatory input. So now if we want to summarize the attack on Chasqui, these are the results we got. So Chasqui has 2 versions, the first proposed one on 8 rounds and the standardized one on 12. We have also 2 cases, whether or not we respect the data limitation to 2 to the 48 or not. We can see that the data limitation here does not change much for the attack. And if we compare with the naive attack, which is quantum exhaustive search of the key, we can see that we actually do much better because we gain roughly 2 to the 15 in terms of total number of operations and 2 to the 25 in terms of total depth. So at the expense of a slightly larger memory cost. So now I'll switch to the conclusion. So what this work told us is that first, for the example of Chesky, but also for the example of Prince, that I did not detail, the attack is really competitive against exhaustive search. We have significantly below in terms of depth and number of operations. It still has this limitation that it requires a large amount of classical data. In terms of memory, it was a good surprise that the amount of required qubit does not blow it. So it's roughly to the 10,000 qubits, which is large, but not in the realm of purely theoretical attacks. This is something that we could hope to have with a powerful and scalable quantum computer. Of course, as we're roughly in the order of 2 to the 50 deaths, it will not be a near-term quantum attack. It's more of a long-term concern. And finally, it really, in order to apply it, we really need to have an Evan-Mansor-like structure. So it really requires a structure in the cipher. We can also have a look at the limitations of the attacks. So first, the optimization that I presented on Chesky can be done on many other ciphers, but they are really limited by the diffusion in the cipher. And in particular, if we have a very large number of rounds, for example, in Elephant, then it becomes a negligible gain. So we went from 25% to roughly 1%. And if we have a look at what makes the attack not work, we have a few points. So first, data limitation can be an issue. For Chesky, it doesn't change anything, but for Elephant, which has a larger state, it does. If the cipher has a state size that's larger than its key size, then it makes our attack comparatively worse if we compare with the quantum exhaustive search of the key. So this is the case for Elephant, for which the attack is not really competitive with exhaustive search. And finally, there's also another way to make it not work, which is to avoid the required structure. So this is the case, for example, for Prince v2, which is a recent proposal for a block cipher that's almost like Prince, but does not have the same structure and for which the attack does not apply. So now this is our final slide with a summary of our result and a comparison with the quantum circuit on RSA and the quantum exhaustive search on AES. Thanks for your attention.
So we have time for some questions. Okay, then I will ask a question. So you mentioned some structures to look at, like Prince, for instance. Have you considered also other structures which might be interesting for your approach, or are those all ciphers you could think of?
Well, we're really limited by the periodic structure for Simon's algorithm. So there are some variations of that, but yeah, for a generic cipher, I do not expect to find anything that we could use to apply this kind of attack.
Yeah. And also for Max, you don't see some applications there due to the mode of operation or stuff like that?
We could have something like that. So we have that for some other works with Simon's algorithm where we have very similar structure and we can leverage it. I don't remember the name of the structure. We have the like Tuxor cascade, for example, for which we even can get some more than quadratic speedup with compared to classical attacks, but it's unclear. Well, it's not that common in the wild. So yeah, we still have some limitations.
So in the meanwhile, some other question? No, okay, then let's thank the speaker again and we move to the next talk. Okay, the next talk title is When Bad News Become Good News, 2 words, unusable instances of learning with physical errors. And Clermont will give the talk.
Can you hear me? Yeah, perfect. So I'm going to present you how we can use physical function to compute learning problems. So first, a little bit of background about learning problems. They are becoming quite a mainstream class of problems that I use for many applications through cryptography, such as MPC. But mainly nowadays, I think their main usage is on post-quantum cryptography. Most of the schemes, lattice-based schemes, rely on LWE, LWR, and ring variance, and so on. So what does a learning problem look like? This is the simpler one, which is called learning parity with noise. Basically, your secret key is a n-bit vector, and you have a uniform public vector, which is also an n-bit vector, and you give a noisy inner product. So in this case, this noisy inner product is binary. You add a Bernoulli error, and given access to the public vector and the noisy inner product, an adversary is not able to neither retrieve the key nor distinguish these things from something that is truly random. Extra. When you want to implement such a scheme, you have to use random number generators, either pseudo-random or physical random generator, truly random. So you can use a random number generator on the public vector and another one on the error. Why would you use different random number generators? Because you don't require the same level of security for both values. One is public, so basically as long as it's uniform, you don't really care if it's weak against leakage or anything, whereas the second one is more sensitive. If an adversary is able, through side channel, to retrieve the error, he may be able to remove it, then retrieve the key. You don't want that. The issue is such... The issue is it can become expensive to protect against side channel attack. It's a weak point. And this is where physical function intervene. The idea is to use inexact computing to directly compute the inner product, but inexactly. So through clock manipulation, voltage overscaling, and such hardware manipulation, you can compute some values with a controlled error. By doing that, you get rid of the second random number generator, which can be expensive. But your problem now relies on a physical function, which we denoted in this case learning parity with physical noise. This was demonstrated in previous papers. And the main issues we ran into were the dependencies, because since it's a physical function, we discover that you cannot control the error as good as if you sampled it independently. So still in the case of learning parity with noise, your inner product is binary, it's either 0 or 1. And we noticed that depending on the correct value of the inner product, we could not manage to get the same error probability, which is an issue because it can lead to filtering attacks and it can lead to more efficient attack. And mainly it's not learning parity with noise anymore, and we want to rely on a solid scheme. This kind of output dependencies, we could not make negligible. So delta value that is shown here was still somewhat noticeable. But in the case of LPN, we got a theoretical reduction that allowed us to ensure that our scheme was as secure as LPN with a loss in the parameters that we could quantify. Everything was working well. There are some other kinds of data dependencies, like input data dependencies, but those are not as bothersome because they are hard to exploit. They can be made as small as we want in the design, so they are not an issue. and we won't talk about this one anymore. And the goal of this paper was to extend the work we did in the binary field to larger ring or field in order to get a learning to do the same work as we did with learning parity with noise, but with learning with error, which is a more used learning problems, so that we can get more complex primitives such as post-quantum 1 and extra. So we wanted to reach larger rings or field. And no, the error distribution won't be a simple Bernoulli. It will be a more complex one. And we decided to target a centered binomial distribution, which is the one that is used in Kyber, famous encryption scheme, post-quantum encryption scheme, sorry. So this is what our inner product structure looks like if it's computed exactly. First, our public vector and our key goes through a multiplication round. Then we add all the values 2 by 2 until we reach our inner product. In the first time, we decided to do same as learning parity with physical noise because it worked well, so why not continue with it? And we applied our inexact computing at some bits of the output value. So for instance, if we want to reach a center binomial distribution of parameters 3, we have to affect the 2 last bits of our values. And then we compared the outcome with controlled errors such that we get as close as possible to CBD3. And we reached this distribution. So in blue is the CBD3, it's a binomial distribution, classical just centered. And in red is ours. And we can notice we did not exactly manage to get the distribution, which is not that big of an issue. But the main issue we run into is a new type of data dependencies that we called mathematical data dependencies. So let me explain with a toy example. Imagine we're just working modulus 4, and the correct value of our inner product is 0. Its binary representation will be 2 bits equal to 0. When we apply our inexact computing, those bits can be flipped. When they get flipped, we can only get an error from 0 to 3. Whereas if we sampled our error incorrectly according to a CBD3, center binomial distribution, the error support should be between -3 and 3. And depending on the correct value of the inner product, we cannot reach all the error we should be able to. So if we look here on the left is what we expect from a regular LWE that is computed with independent sampling, etc. On the right is what we got with our first design. So we notice that the regular LWE, you have all the errors you can get, whereas on the right, the error is not the same depending on the correct value of the last least significant bits of our inner product. This leads, when you look at the whole inner product, to not the same distribution of error. So we don't get exactly what we want. We have data dependencies that can be used with filtering attacks. So not good. We then tried other designs and ended up with this one. The idea is that no, we don't sample, we don't do inexact computing on the output bits, on the bits of the outcome or the output value. We perform inexact computing at intermediate stages of intermediate adder stages, only on the least significant bits. Then the error, so incorrect computation is propagated, and at the end, we still get an inner product that is inexact. We noticed that with this one, we were able to approximate center binomial distribution much closer. And the question is, what happened to the data dependencies? And it went really well because the mathematical data dependencies were canceled, basically. They appeared locally when we performed inexact computing, but then they were adding with independent uniform values, and they disappeared. Considering the other data dependencies, the physical one, like the output dependency we had earlier, it's a little bit trickier because since it's a physical dependency, we could not be sure that there were no coupling mechanism, for instance, that makes the other values not independent. And then maybe the output dependency could propagate and still appear at the end. It was part of the motivation to build an FPGA prototype that could allow us to verify this data dependency thing. So prototypes perform inexact computing with clock manipulation. Basically, what you do is you stop the clock a little bit earlier so that the output value does not have time to stabilize and you have a chance to sample it incorrectly. And by controlling the time when you stop the clock, you can control the error probability. And we observed with statistical tests the output, and we could not notice any data dependencies, which means that the coupling mechanism, if they exist, were small enough so that we could not find any dependencies, so we suppose they cannot be exploited. So exactly what's the use for this inexact computing stuff? What do you gain rather than computing things in the standard way? Mainly it's interesting against leakage because you get a linear overhead in the shares number. You don't have to mask a random number generator. This is mainly due because the inner product is linear, so you can get shares on the key. It's easy. And it's also eminently good against glitches because it's already glitchy. It's kind of the point. What we want to do with it now is extend it so that we can reach useful space, let's say. At the moment, we managed to build a prototype that works on power of 2 modulus ring. If we want to build a primitive with it, we should be able to reach a prime field, some ring version for RLWE. We should be able to reach different multiplication algorithms, such as NTT that is used in many schemes, and also different error distribution, because CBD is good for Kyber, but if you want to do dilithium, for instance, who may be the next post-quantum standard for signature, we need a uniform noise. So in this figure, in green is what we already have, in yellow is what should be relatively easy to achieve with small adjustments, and in orange is what is a little bit trickier, and the error distribution part is not totally figured out yet. Also, there's still a bit of theoretical work in order to ensure that the data dependencies are not an issue. First, understand the amount of witness they create, and maybe have a theoretical reduction, same as LPPN, but for learning with physical error. Thanks for your attention. I was a bit too quick, but better this way than the other, I think.
I think that's okay. Yeah. Well, let's thank the speaker. So now we have time for several questions, actually.
Exactly.
Thank you for the talk. It's okay. Yeah. Is there a relation between the error probability and the decryption failure probability?
Sorry,
So you showed the error probability which you had.
this one?
Yeah, maybe in the beginning there was this.
Yeah, the output dependency of the error probability. Yeah.
So is there a relation between this and the decryption failure? So in case of Kyber or for any scheme, do you think there is a relation between these two?
In case of Kyber, we won't have the issue because Kyber is computed with learning with error and with learning with physical error. Thanks to adding the error at intermediate stages, we don't have such output dependencies, or at least they are totally negligible. This one really appeared with Bernoulli distribution because we had to compute in the output stage of the inner product. So it won't affect the decryption rate, the decryption failure probability of Kyber.
Okay, thank you.
Okay, I think we have a question online. I'm not sure. Yeah. So you have mentioned the power of two modulus rings. Can you give examples of those rings, excluding Saber and Entro?
So question was, I didn't understand it.
Sorry, once more. You have mentioned the power of two modulus rings.
Yeah.
Can you give examples of those rings, excluding Saber and Entro?
For concrete application, I don't think they are, but it was not the point for this paper yet. We just wanted to have a prototype that demonstrated that we could have some operations that are similar to learning with error. Actually, we even did it on, I think, 128 elements, so really small ring that won't have any concrete application. If we want to scale it up, we may have to consider some other hardwares, and it will be extending the design space is still a lot of work. This one is just showing that it is possible to do it and how it will behave when leaving the binary field.
Okay, thank you. Some more questions? Okay, then let's thank the speaker again.
Thank you.
And we're moving to the last talk of this session, and afterwards we will leave for lunch. Yeah?
This. And this can click.
So the last talk of this session is about a fast, large, integer, extended GCD algorithm and hardware design for verifiable delay functions and modular inversion. And here we'll give the talk.
All right, thank you. Hi, everyone. My name is Kavya Sridhar, and I am a fourth-year PhD student at Stanford. Today, like was mentioned, I'll be talking about our work on a fast, large integer extended GCD algorithm and hardware design for various cryptographic applications. Extended GCD is a fundamental operation in number theory and computes Bezier coefficients that satisfy the Bezier identity as shown here. This has wide-ranging applications in cryptography, primarily to compute the modular multiplicative inverse, which is useful for applications such as RSA, elliptic curve cryptography, Al-Gamal encryption, and so on and so forth. As a result, a lot of work has been spent on fast GCD algorithms in the 80s and 90s. However, there has been, until recently, very little development further in this domain. However, two recent developments suggest that there is a need for increasing fast extended GCD implementations. The first is the realization that constant time extended GCD can be faster than Fermat's Little theorem for modular inversion for elliptic curve cryptography, such as curve 25519. The second motivating application is this increased interest in squaring binary quadratic forms over class groups as a verifiable delay function. VDFs, verifiable delay functions, are useful for consensus protocols. And for this particular VDF, XGCD is the primary bottleneck, taking 91% of the execution time when profiled in software. So for the two applications we consider, there are distinct application requirements. For the first one, we are interested in constant time 255-bit XGCD to protect against timing side channel attacks. And for the second one, we are interested in non-constant time 1024-bit extended GCD since the inputs are not secret. So to understand the current space and what current literature exists, we decided to look at prior work. And all of our performance graphs here have clock frequency in gigahertz on the x-axis and the number of cycles on the y-axis. So their product gives us total execution time, and we can draw these constant performance lines. So if you have a clock frequency and a cycle count, and you have a clock frequency that's 10 times higher, you require a cycle count that's also 10 times higher to draw these constant performance lines. And as a result, faster performance, better performance, faster execution time corresponds to lines that are towards the bottom right of these graphs. And that's where faster, better points are. So if we look at the actual space, we see on the left for 255-bit constant time extended GCD, there are two recent software works, the first of which, the Bernstein-Yang algorithm, was presented at CHES in 2019. And then we also see there's an FPGA prototype of that algorithm. However, there are no ASIC points in that space. On the 1024-bit side, we see that there are two ASIC points. However, the fastest ASIC is twice as fast as software. So what we realized from these graphs is that not only are there not very many hardware points in this space, the points that do exist focus on iterative division-based algorithms for this computation and provide point solutions for either constant time or non-constant time execution. So we instead decide to explore the broader design space across three different axes. First, target platform, then iterative algorithm operation, and finally, application requirements. And we find that in contrast to all prior hardware papers that choose iterative division-based algorithms, in the hardware context, we can yield higher performance with iterative subtraction instead. And we further provide a unified configurable design that supports both constant time and non-constant time execution with the same ASIC unit, which can be useful because ASICs can be expensive to deploy. So first, the target platform axis, hardware versus software. We first realized that the number of iterations in an algorithm is algorithm dependent and platform independent. So the same lessons from software can be carried over to hardware. However, when we look at the time per iteration, we recognize that software implementations are inherently constrained to using a processor's ISA, whereas hardware is not. So in hardware, we have more of a flexibility to design fast, wide, custom data paths. Maybe it's not muted on Zoom. So in hardware, we have the opportunity to design fast, wide, custom data paths, which allow us to achieve extremely short iteration times. So we recognize that this fact about hardware opens up the opportunity to accelerate algorithms with simpler operations such as subtraction with fast iteration times, but maybe higher iteration counts. So for the second axis, GCD algorithms. GCD algorithms are by nature iterative and repeatedly apply GCD preserving transformations to reduce the inputs to the actual GCD and zero. And so we see Stein's family of algorithms are subtraction based and repeatedly subtract. When inputs are even, Stein's algorithm also divides by a factor of 2.
When it was not.
On the division side, we repeatedly apply division-based transformations. So we now compare the number of iterations for the worst case inputs for these algorithms, which we use for our constant time implementation. And we see we actually choose to use an optimized point in the Stein family of algorithms, which is called the 2-bit PM algorithm from 1986. This algorithm divides by 4 instead of just dividing by 2 whenever it can.
Right.
And we see that the cycle counts are actually quite similar between the division and the subtraction-based algorithms with these algorithms here. And this means that in the worst case scenario with worst case inputs, subtraction-based algorithms are likely more competitive because they have simpler operations, but similar iteration counts. In the average case, we see that the 2-bit PM algorithm requires 1.6 to 2 times the number of iterations compared to Euclid's algorithm. And since all prior hardware works had chosen to implement Euclid's algorithm, we were curious whether the iteration time for 2-bit subtraction-based PM algorithms could be at least twice as fast compared to division-based algorithms, meaning that they would lead to better performance overall. So to understand what the iteration time looks like, we needed to understand the operations in extended GCD. And typically GCD algorithms introduce these 2 additional relations on the slide here to compute extended GCD. And the operations required essentially are to compute these coefficients. So in order to compare iteration times, we look at the critical path of operations. In software, there's typically 1 data path of operations. In hardware, you have multiple concurrent data paths. And the longest data path is called the critical path. And so we wanted to analytically compare the performance ceilings of the critical paths between the 2-bit PM and Euclid's algorithm. So for the 2-bit PM critical path, the most complicated operation is subtracting the two inputs and dividing by 4. And to compute the extended GCD coefficients, this translates into a simpler subtraction and then a subtraction by an odd coefficient sometimes, and dividing by 4. The details of this are in our paper. The important thing to take away from here is that we need to do 2 subtractions followed by a divide by 4 for this algorithm. On the Euclid side, we need to compute the quotient and the remainder. And since the quotients tend to be quite small in Euclid's algorithm, the fastest way we thought of to do this is to approximate the most significant bits of the quotient using the most significant bits of your input. The fastest way to do this is using a lookup table, and we estimate that as 0 delay for an optimistic estimate. Then to actually compute the remainder, we take the 6 bits in this example of the quotient we've estimated here, multiply by b, and subtract to get our remainder. We see that since we're just multiplying by bits, which are 0 or 1, this really just corresponds to shifting or choosing 0 and then doing the subtraction. And what we realized from these critical paths is that our critical paths primarily consist of additions. And the fastest known adder primitive that we can use is a carry save adder. So typically when we add our bits, propagate carries, and continues on and on. However, a carry save adder computes the carries and stores them separately, and each number is stored in this redundant binary form where you have the sum and the carry both stored. As a result, during the execution, you actually don't know the value of your numbers, but at the very end, you can recover the true result by adding your carry save form numbers. As a result, each bit is computed using a 1-bit adder, and we have a constant delay. So no matter how many bits there are, the add takes the same time with this redundant form. So in the 2-bit PM critical path, we see that we need to add together 2 numbers, which in redundant form becomes 4 numbers. And our last number is actually just a constant, so we are adding 5 numbers together. With 3 input, 2 output carry save adders, this requires 3 carry save adder delays. On the Euclid side, we see that since A and B are now in this redundant binary form, to actually estimate the 6 most significant bits of Q, we need to get A and B, the most significant bits, out of the redundant form and estimate that. And that requires a 6-bit normal carry propagate add, which can be estimated as 3 carry save adder delays. To actually compute the remainder, we need to add 7 inputs, each of which are in a redundant form. So this turns into 14 inputs and ends up requiring 6 carry save adder delays. So we can see that the Euclid critical path requires at least 9 carry save adder delays. And the 2-bit PM algorithm is at least 3 times faster compared to Euclid's algorithm when examining the critical paths. And since it only required twice the number of iterations, we find that in contrast to all prior hardware papers in this space, it will be better for performance to use the 2-bit PM algorithm and start from there. So finally, we considered the application requirements axis. And like most GCD algorithms do for non-constant time implementations, we reduce our inputs until one of the inputs is 0 and take the other input as the GCD. For constant time, we have a configuration bit, which when set, allows the execution to run for the worst case cycle count. Note that this will still be functional because whenever the algorithm should have ended and one of the values is 0, the algorithm will keep dividing 0 by 2, and so we'll still get the correct results at the end, even if we run for longer. And since A and B are in this redundant representation, the important thing about our work is we don't actually know when the numbers became 0, and we can run for the worst case. So if we go back to the optimal design space, we see that it is more efficient to use subtraction-based algorithms, and we're able to provide this configurable unified design for extended GCD. So now that we had found which path in the design space was the optimal path to follow, we wanted to further add some tricks to improve upon our point within this space. So if we look at our actual accelerator execution, we start with a pre-processing step. Then we actually have the iterations loop, which takes the majority of time. And then this is followed by a post-processing step that recovers our results and converts out of redundant binary form so we can actually present our results. So one of the first things we had to do was ensure that our results were correct when in this redundant form. And whenever we shift, we need to ensure we preserve the sign bit, and we also ensured results were not incorrectly truncated. More details of the circuits we use are in our paper. The second thing we wanted to look at was ensure that the additions, the carry propagate additions in our pre and post processing steps did not limit our clock frequencies. And so we allocate 4 fast clock cycles for the pre-processing and 8 fast clock cycles for the post-processing steps to ensure this. We also similarly for our termination condition in the average case to check when our inputs are 0. Spread this across 4 cycles to ensure that this once again does not limit our clock frequency. This means that every 4 cycles, we can check when our value is 0, and we at most end up adding 3 cycles to our overall execution, which when we're running and taking 400 to 1,600 cycles for our bit widths ends up being quite negligible. And then finally, we work to minimize our control path overhead. And so we pre-compute control signals in a previous clock cycle. And we also use late selects and duplicate computation to ensure this does not limit our frequency. So our actual ASIC in 16 nanometer has the following critical path. And the main highlight here is that we can see the path looks like what we expect. We've got 3 carry save adder delays, followed by some logic to shift correctly in carry save form, followed by some logic to mux between our options and use late selects to select the correct update. And then we pre-compute some control logic. And we see that since we used carry save adders, we actually have between our 255-bit and our 1024-bit design, quite similar clock periods and quite similar clock frequencies, showing that our design will scale at a very similar clock period for even higher bit widths, and it's relatively bit width independent. Since our 1024-bit design is larger, physical design becomes a little bit more complicated. And with our actual numbers, we see that the clock periods have a slight difference, and we're able to achieve 4 gigahertz for our 4.5 gigahertz for our 255-bit extended GCD design, and 4 gigahertz for our 1024-bit one. Note that these are post-layout numbers for a fabrication-ready, tape-out-ready design. So if we actually go to our comparison, we see that compared to the software, our 255-bit constant time extended GCD is 31 times faster. And importantly, it's the first ASIC point we're aware of in this space. On the 1020, and we also see for the direct FPGA comparison, which we wanted to ensure that our speedup was due not to just doing an ASIC, but also because of our algorithm, we see compared to the Bernstein-Yang prototype, our design is 45 times faster. Now on the 1024-bit side, we see that our work is 36 times faster compared to software, and we're 8 times faster than the previous state-of-the-art ASIC. And this is primarily due to the fact that we chose to use iterative subtraction instead of iterative division. And again, for a direct FPGA comparison, comparing numbers on the same FPGA as the prior fastest work we were aware of, we see that our work is 2.7 times faster. So our design, aside from the individual extended GCD speedup, also has further implications at the application level. First, for modular inversion for Curve 25519, it supports the progression in the state of the art from Fermat's Little theorem to using extended GCD, and further explores the opportunity to consider point multiplication algorithms that use more inversions, which were previously avoided because inversion used to be the bottleneck. The second thing it does is for this particular verifiable delay function with our speedup of a 36 factor, it informs reasonable security levels and input bit widths that need to be used. And finally, this may be useful for other applications, and we're really interested in learning about further applications that may be useful here. So if you're aware of anything or interested in learning more about our work to apply, please let us know. We would love to hear about it. Finally, our work is open source and available at this link here, and I'd be happy to take any questions. Thank you.
So are there any questions? Or maybe some applications?
Yes, we're always looking for ideas. Yes.
So for the 1024-bit implementation, what was the
Yes.
size of the carry save adders?
Yes, so the carry save adders are n bits, so 1024, 255-bit. The important thing is that since each of the bits are 1-bit full adder in parallel, the timing is constant regardless of the bit width.
Right, right. So when you did a comparison between your implementation and previous ASICs. In terms of like absolute number of clock cycles, if you want to scale essentially, let's say take the size of the adder out of the picture, and also take the advantage that you got because of the technology out of the picture.
Sorry, could you repeat that last part again?
Yes. If you take the clock frequency,
Yes.
if you don't take that into equation, because obviously in 16 nanometer, you are getting advantage from the clock frequency. And plus, when you compare your design with previous ASIC implementations, we do not know how big.
Yes, that's a
ADAS
good
they use,
question.
right?
So actually the numbers we report are technology scaled. So we scaled the prior ASIC in 28 nanometer to 16 nanometer for a fair comparison for our speed up results. So you'll notice that actually in the graph here, our speed up would be higher if you compare the absolute numbers, but we've scaled that down. And then we also observed that actually we have a clock frequency improvement compared to the prior work with the scaling, but we also have a lower cycle count. So if you look at the ZST plus 20 paper, that's the prior ASIC. And then ours is the orange triangle on the right. And you can see that it is lower on the cycle count axis and to the right on frequency.
Got it. Thank you.
Yes. No problem.
Some more questions?
Thank you for your talk.
Yes.
I was wondering, so you focus exclusively on latency, and I'm assuming VDFs are probably designed to counter this, but is there any opportunity for pipelining, maybe over different inputs in the protocol or?
Yes, that's a good question. So the way the VDF application is constructed, there's actually one extended GCD. So pipelining would not be useful here because that's only useful when you're repeatedly doing it, right? But unfortunately here we're doing the extended GCD, did a bunch of other operations, and then we come back to do the GCD. So we can't really take advantage of pipelining for this particular application. But you're absolutely correct that if there was an application that did, we could add pipelining in here and then use the same ASIC with the pipeline results.
There's no protocol you're aware of where it's useful to compute like multiple VDFs in parallel and use that to pipeline the circuit?
At the moment, I'm not aware of it, but if you are, or if anyone is, please tell us, we'll do it. And we'd be happy to work on that.
I'm not, but thank you.
Yes, thank you so much for the question.
So I think we have one more question over there.
Yes.
Yeah, so I think you were mentioning ZST as a ASIC example, which what are the capabilities of that and how you are sure that that is state of the art ASIC available in this space?
Yes, definitely. So we looked up the prior literature. VDFs were introduced in 2018 really recently. And since then, there have been 2 STIP papers on ASICs, and actually both by a similar set of authors. The Z is the same in both these ASICs. And so these are the papers we were aware of, and we saw that this implementation they had done in 2020 was the fastest. So this is basically the current state of the art. It's quite sparse since this is a relatively new application. Did that help? Okay, great.
Okay, one more last question. Okay, then let's thank the speaker again.
Thank you
and
so
have
much.
lunch.
Thank you.
I think this one is audio.
You just hold back up.